All right. Hey, folks. My name is Andrew Owen. I'm with the OSG facilitation team, and we're going to be talking about how to deploy Python on the OSPool today. So this is going to be mostly slides. I do have some a short demo for how to set up the software, but for the most part, this is just communicating some of the knowledge and experience I've gained as a facilitator and as a Python user for folks who are interested in deploying Python on the OSPool. So we are the research computing facilitation team. We are here to help you out when it comes to going from your computing, your laptop to computing on a large scale system like the OSPool. Um, So there's myself. Danny Morales is also on the call as well, so he'll be answering questions you put in the chat, and I'll try to keep an eye on it as well. But if you send us an email to our support address, any one of us may reply, or if you stop by our office hours, you may see any of us. So we are recording this call if you hadn't noticed. We do welcome any and all questions, so don't hesitate to ask. You can also put them in the chat. If you're not comfortable asking a question while we're being recorded, that's okay. There'll be time at the end of the training for you to ask your questions. There is not a hands-on part to this particular training, so I forgot to edit this slide, but in the future, I do have plans for making this a bit more hands-on. Okay. So our primary learning objective here today is to understand how to deploy Python-based calculations on the OSPool. So at the end of the day, you're working with Python, you want to do something at a large scale, and the OSPool can help with that. So we're going to talk about the pieces between running the Python on your laptop and running the Python on the OSPool to try and help you bridge that gap. So there's a few parts that come into this. First, we're going to be looking at what are the characteristics and constraints about working on the OSPool. It's a little different than working from your laptop. A lot more, I'd say, moving parts, a lot more things to consider. One of the early stumbling blocks for folks who want to get started on the OSPool is deploying their software. And so we're going to talk about the methods of deploying Python dependencies on the OSPool to help you get started. And then identifying changes that you want to make to your existing Python code in order for it to work on the system. So the script that you may use on your own laptop may not be properly formatted for working in the distributed computing environment. And we'll talk about some of the changes to make things a bit smoother. And then I'll also briefly talk about how to deploy Python code that you're actively developing. Oftentimes, researchers, you're developing Python code, and you want to see how it does for this large simulation that takes a while to run. You use the OSPool to run the simulation, but now you got to incorporate changes. How do you do this sort of workflow in a efficient way? In case you didn't notice, there is slides available at the URL. Danny's put it in the chat, and you can also see it at the bottom left corner of the screen. All right. So the agenda is basically to take those learning objectives in series here. So we're going to talk about the OSPool, talk about setting up Python and dependencies, how to script for working on the OSPool, as well as how to develop and how to move forward with next steps. All right, the OSPool. So we're going to take a step back and think about what is it that you're trying to do. And usually at the end of the day, any computing problem that you can't run on your computer, in some form or another, it needs to become a list of calculations that need to be run. And the way that the OSPool tackles this problem is to take those lists of tasks that you want to run and send them out to many different computers. So instead of having one, very large computer or a very expensive cluster, we work by connecting with lots of different individual computers, usually clusters at campus levels. But we distribute out the tasks using HG Condor as the manager, and the results are executed on these remote machines and things come back. So this is a little different paradigm from traditional supercomputing or high performance computing. But at the end of the day, the things that are going to work best on the OSPool is something where you can do this sort of delineation. You can split it up into smaller pieces and send those out to run on separate computers. The OS pool itself is, you could think about it as a virtual cluster. So it's not hardware in a room, in any one particular room. Rather, it's hardware all across the country. So there are lots of various campuses and institutions who have invested a lot of money into computing systems for their own use at their facility. Um, and they want to make sure that they're getting their money's worth from that huge investment. And local researchers aren't always using the machines. It's just the nature of research, right? You don't always have things that you need to run immediately. But you still have that very expensive hardware that you're paying money to run. You want to make sure that it's being used. So the idea of the OS pool is when those resources are not being used, when they're extra, or some portion of them has been set aside, any user as part of the OS pool can run their work on those extra resources. So what the OSPool is really about is making sure that these resources are used efficiently at all times. Um, but it provides a central location for you to go to, so you don't have to have an account on each one of these different clusters and log into each one separately. You can just submit jobs to the central OSPool system, and we figure out all the details about where to send it. The OSPool is free to use for US-based researchers. If you're interested in accounts, I'll have some info at the end of the presentation. You can also check out our website for more information. So this is a pretty distributed system. This is operated by the OSG consortium. So basically, we're the folks that handle the central communication and the system for doing this distributed work. And while most of our computing systems are based in the US, we do have some collaborator institutions outside of the US that are connected with the OSG and the OS pool. In general, unless you're part of one of these collaborations, your work is going to stay in the US, but there's a lot of geographic distribution in terms of where the OSG and the OS pool operates. So, what does that mean for you as the end researcher? Well, I've already hinted at this earlier, but the OSPool is a good fit for high throughput computing workloads. So because we have so many computers in the system, you can run, dozens, 100,000, a million jobs on the system. And, those could go all over the country in all sorts of different places, and utilize those extra resources that other researchers aren't using at the moment. And to best take advantage of this, your work needs to be able to be distributed, and ideally it's going to be open. So the jobs that you want to submit to the system, you want them to be relatively short, or at least resumable. And here by short, I mean 10 minutes to an hour is probably ideal. For technical limitations, we can't go under 10 minutes. But we also, because these are donated resources, we can't go for days at a time. The jobs that you want to run, they should each have about the profile, the resource usage of your laptop. So you'd be able to run this on your laptop, or run the calculation on your laptop, but you'd have to run 100,000 of them. And that's the sort of problem that the OSPool is really good with. Data movements in this distributed system is a bit limited, right? We're sending the jobs all across the country, which means we also need to send your input data across the country. We need to send your output data back in the other direction. And so this sort of pipeline isn't great for large data per job, although you can get a lot of data processing done if you can keep the total sizes pretty low, or the individual sizes low. And then lastly, jobs and software. So the software and the data used in the jobs, ideally it's open. And there's a couple of reasons for that. One, with open source software, you don't have to worry about setting up a license. A lot of licensed software have restrictions about the physical location or number of machines upon which you can run their software. So it really depends on what the license is, but for the most part, you're going to have an easier experience if you just avoid licensed software altogether. And then this is a very distributed system. You're trusting us, and we're trusting the campus that is donating the computing resources that and that there isn't a security breach anywhere in that chain. So we don't meet the legal requirements for supporting HIPAA data or any other legally protected data. And in general, you should just think about good data security. Is this something that you'd want a random system administrator in picking the state at random here, Oregon, to be able to access by looking in on their computer? So, okay. All right, so that's how the OSPool is sort of sets the stage for the type of work that we can do. Next is how do we get our software up and running to handle that work? And so here we're going to talk about deploying Python and dependencies. First, though, is okay. What do we have out on the OSPool? Um, so when I grabbed these, there was something like 30,000 machines out in the OSPool. And or it's more like 40,000 cores, CPU cores, so it doesn't quite correlate to machines. But we got a lot of different operating systems on the OSPool. So here's a breakdown from when I checked last week. Quite a few CentOS machines. Most of them are CentOS 9, but we got some Debian and Ubuntu in there as well. And then in terms of the Python that we have deployed on the system, so as far as I could tell, almost all the machines in the pool had Python on it, at least when I checked. And they report this Python version. And so what we're seeing here is that by and far, most of them are running Python 3.9, patch version 21. Now, there's a few other versions of Python on the pool, and you can expect over time that these versions are going to change as well as, you know, the later releases become more stable and are adopted more by the community. You'll see this distribution shift to higher and higher versions of Python. And then where the real sticking point comes in is what are the Python packages that are installed? So Python has a standard library, and if you're working from that, you should have a pretty good experience overall. But if it's not in the standard library, then it's kind of up in the air what we're going to have installed. From my peek around the different sites that contribute to the OSPool, and this was just the 57 that I was able to get a job to run within, 10 or 20 minutes. I saw quite a few different versions of NumPy out there. Most of them NumPy 1.23. But you can see there's a couple different versions as well. There was even a couple machines that they didn't have pip. They had Python, but they didn't have pip. So I couldn't use pip to check and see what packages were installed. I did a glance through the different package lists. The NumPy was just a selection of what my test job was looking for. I glanced through things, and something that I noticed is, some of these sites had SciPy and pandas in addition to NumPy, but most of them did not have pandas. So they had SciPy, but they didn't have pandas. And that might be kind of surprising to you as the researcher. If you're used to working with pandas, it seems like, well, why, of course, why don't they have pandas installed? Um, but not everyone's doing data science, and not everyone is, especially the system administrators who are running these machines, are not necessarily interested in having pandas installed globally on their machine. And from a look over that list, I mean, SciPy is probably the most complex package in the stack that I was able to find. More than that, or I guess I don't have a good way of saying that. From my experience with using Python, there was only about 5 or so packages, and I'm like, oh yeah, that makes sense to have installed. And the other ones I'm pretty sure were just part of whatever's required for the standard library and the standard deployment of Python. What that means for you as the researcher, though, if you want to use SymPy, which is something I used in my own research. That was not included in any of these lists. If you have something else that you want to use that's even more obscure, it's almost certainly not going to be in the list. And so the packages that you want to use are not going to be on these machines, and that in turn sets up a problem for you for how do you execute your script that relies on a particular package. So the way that we recommend this on the OSPool, we recommend that you use something called a container. So if you're not familiar with what a container is, it's a highly portable, um, self-contained operating system that you can send to another computer, and it will replicate the software environment that you set up inside, regardless of what the underlying operating system of that host machine is, or whatever software it may have installed on there. So it's a really powerful way of getting the software you want, where you want it to be, um, in replicating your software environment. So that's what we recommend, is using a container. We support Apptainer on the system. If you use Docker, there is a way to switch to convert from Docker into Apptainer. There are a couple other ways of deploying Python, but I'm not really going to talk about them. The first one I guess I sort of have already, which is the using the Python that's already installed on the machine. If you have a very simple script, a very robust script that is backwards compatible to, a couple of different versions of Python and uses a standard library, you may not have to actually worry about any of the things that I'm about to talk about. But again, you're relying on us that, our versions are going to continue to be compatible, or not even necessarily on us on the OSG team, but you're relying on all these contributing institutions that they're going to keep using Python 3.9 for the foreseeable future. And that could be a problem if we upgrade and your code doesn't. It is possible to pre-compile the code that you want to do manually and then deploy it. So that's essentially making it portable without using a container. That's an advanced thing. It's how we used to do it, but honestly, it's really complicated. I'm going to strongly recommend that you use a container. It has a lot of benefits and is no more difficult to do than the other methods. So containers is a entirely separate training. So I'm not going to go into all the weeds here because I want to focus on the Python part of things, but there's a lot that can go into working with containers, especially if you're someone who's new to working with containers. It can seem a bit scary, it can seem a bit intimidating. We have guides on our website. We've got this previous training that we have given. And we're happy to help you in office hours or over email figure out how to set up your container environment. The general process for using a container, the first step is to figure out what are the installation and instructions you need for setting up your environments. And you put those into what we call a definition file. So you're defining what you want the software environment to be that the container is deploying, and that goes into a file. And then there's a process of converting those instructions into the actual container image. So we call this building the container. You take those installation instructions and you run a particular command. It's going to then install all of those things you asked it to inside of this portable environment, and that is the image. Then for running jobs on the OSPool, you take that container image, you give it to htcondor, and you say, here's my image. And now your job is going to run inside of that software environment whenever it starts up on one of these contributing sites. So htcondor handles a lot of the messy details about how to actually launch the container and use it inside of the job. You just have to give it the image, but you have to give it the image. And you have to decide what software you want to go into that image, and you have to decide how that software gets in the image. So a lot of working with containers is actually just figuring out what is the right definition file to use for the software that you're trying to use. So I have some examples here. I'm not going to go into a ton of detail because, again, there's a lot of stuff that goes into containers. I recommend looking at the container training. But here's I'd say the most straightforward example is you just want to pip install something on a particular version of Python. And so here is an example where we're going to use Python 3.13 as the starting point. And then I'm going to have it install particular versions of NumPy and Pandas. So I make sure I have the packages I need and I have the versions of those packages that I need. You don't necessarily have to pin the versions in this step, especially if you're just getting started with that package and you don't know what versions you're going to use yet. But we generally recommend it to make sure that when you build the container, it's reproducible. If you come back and build it a month from now, if you have the versions pins, when you build it a month from now, you should still get a working container that's compatible with your script. If you don't pin the versions, there's a risk that whatever the latest version is introduces a breaking change that your script can't handle and your workflow stops working. So, like I said, this is the most straightforward. I got a couple more examples here, but I'm not going to go into too much detail other than to highlight, yes, it's possible to do X. So here's an example of using Conda as the installer for setting up your software. So this is using the open source MiniForge version of Conda. And then in my definition file, here's my Conda install command. And yes, there's a way of doing this with an environment.yaml file and setting up multiple environments and all sorts of other things. But again, I'm not going to go into too much detail. And you can even do this from scratch. So let's say you need to, I don't know, compile a custom version of Python or something. That is something that you can do. So you can use the Linux package managers to install your dependencies. Here I have it installing Python, but in principle, you could do a manual, make, configure, compile of your Python program and Python that you're developing. GPUs is a common one. So, PyTorch and things like that. This particular example isn't actually trying to install PyTorch, so there's nothing special going on here. But this is using the official NVIDIA container as the starting point, which has everything you need for working with CUDA, in which turn you have everything you need for doing machine learning on a NVIDIA-based GPU. So there's a whole nother training on working with GPUs on the OSPool. I recommend you check that out. Links are in the slides, and my colleague put them in the chat as well. Okay. So once you figured out what goes into your definition file, then you need to create the container image. We have instructions about how to do that on our website. This is going to create the image file, which is a .sif file. You want to place this into your OSDF directory. These are typically large files. We want to use OSDF for transferring the large files. OSDF is also really good about reusing large files. And once you set up a container, that reuse can save you a lot of network transfer, all in all. And then in your submit file, you add one line. That's all you need to do is one line in your submit file that says, here is my container image. HTCondor will handle everything else that needs to happen. So you don't need to do a container run or container execute command. You just put in your executable file or in your command, what is the command that you want to run inside of that container software environment. HTCondor handles all the rest automatically. There can be some hiccups with that, but that's what my team is here to help you with. All right. And to introduce a little bit of excitement into the day, I am going to do a live demonstration of building a container that has Python. So in the chats, please suggest a version of Python that I should use and some packages that you want me to install. So I'm going to pick a couple of those to work with, and we're just gonna, I am gonna curate it a little bit. I'm not gonna go too crazy with the packages, but you're welcome to put it in there. And then I'm just gonna log into AP40. So I'm logging into one of the OSPool access points. This is how you submit jobs on the system. I'm gonna confirm my identity. And there we go. All right, so I'm logged in here. On OSPool, currently we have you build the containers on the login server. It's not ideal, but it's what we have. Instructions, you can just follow the instructions on the Apptainer guide here, and I'll drop that in the chat real quick. All right, so you got to come up with a definition file. I'll give you some time to come up with some packages here. Before you try to build the container, we do need to make sure that these environment variables are set, because otherwise it'll hurt the performance of the login server. And you can see a big warning about that. So I'm going to make sure I run these commands, and you can confirm that it's set if you want by running something like that. Okay, so I have it set. Great. Okay, so then I need to come up with a definition file, and so that's I'm gonna go with what's in the chat here. Okay, only a few things posted. Okay, I'm gonna go just to keep myself organized. Let's see here, Python training.def. All right. So I build a lot of containers. I'm familiar with what the syntax is. You can probably just copy and paste and then edit from there based on what we have on our website. All right, so request for Python 3.12.7. I'm just going to go with 3.12. So if you do need the patch version of Python, I think you can specify that here. But in general, the purpose of the patch version is to fix any security flaws that may have been introduced, but without breaking any changes other than whatever the bug or security issue was. So you usually want to have the latest patch version if you can. So I'm going to do Python 3.12, and we got a few packages here. So in the post section, I put my installation commands. And then we got, okay, pandas, numpy, scikit-learn, and cowsay. I am going to avoid scikit-learn just because I think that involves, well, no, let's try it. Let's see what happens. Hopefully that is the right syntax for doing pip install. If it's not, you should correct me in the chat. Okay, so here, I'm not including any versions. You'd be welcome to, but if I were getting started from scratch, this is probably what I'd do. All right, so I have the definition file, and then I'm going to, and I set those environment variables earlier. So now I'm going to run the container build. So apptainer build, I give the name that I want the container to have. And so in this case, this is going to be, I'm going to keep it consistent. Python training.sif. SIF is the container extension. And then I'm going to give it the instructions for how to create that. And so I'm going to drop that. And here, I'll try not to go into too much detail, but I don't have much else to do while it's running. What we're seeing here initially, some progress bars is downloading the original Python image. Now we see the typical pip install output that you would see if you were doing this locally. It is going to give me a warning about running as root. When you're building a container, you can ignore that warning. If you are installing Python packages on your own computer and see this warning, you should probably listen to it. And now it's finalizing, it's creating this portable environment, and there we go. All right, so did it work? Well, that's a great question. Right now, I'm on the login server. I'm using the host software environment. So I'm using the software environment of the login server. And here, if I load the Python 3 terminal, I see that we're using Python 3.9. And if I try to import cowsay, I'm going to get an error. If I try to import numpy, I think that might work. Oh, nope. I thought we had numpy. And so if that didn't work, then I'm sure sklearn. Oh, I actually don't remember the naming with s scikit-learn just because it's a little funky. So not able, I don't have NumPy, I don't have Causa. This is Python 3.9. So this is what's on the on this machine by default. So I'm going to exit the terminal. I'm going to do a special command to launch the container image. This is not something that you need to run as part of your job. This is just how we poke around and test things out. So here my prompt is changed to apptainer. And if I load the Python 3 terminal, now we see I'm working with Python 3.12. Here the patch version is 12. So there's been 5 releases since 3.12.7 that have fixed bugs or security issues. And then I can import Causa, I can import NumPy. I will try to, nope, I don't remember what it's called. But then I can use Causa, cow, hello from Madison, Wisconsin. And there we go. And with NumPy, let's see here, I could do NumPy dot array 163, and now I have an array. So I now have a container that I can use that has NumPy. It's got pandas. Oh, that was the other thing. I should import pandas. There we go. Oh man, it's been a long time since I've used pandas. Da, da, da. We're gonna try this. I do not claim that this will work because it's been probably a solid 3 years since I've used it. Oh, there we go. I guess I still remember a little bit about pandas. So now I have pandas. So this is all being executed inside the container environments. And when you include this container image in your HD Condor job, you will have the same functionality. So if you're calling a Python script that calls pandas, your script in your job, when you provide this container image, will also be able to use pandas. Something I do want to caution you against, though, is running intensive commands on the access point here. And wow, Danny read my mind. He just put some text in the chat about what I'm referring to. But basically, where you log in is where you log in. It's where everyone logs in. And if you run an intensive program on the login server, you can cause issues for everyone. So anytime you got something that's intense, and by that I mean it's going to take more than a minute or two to run, or it's going to use a lot of RAM or a lot of CPU, you should submit an HD Condor job that will handle it instead. So last thing that I'm going to do, I'm going to move my container image into my OSDF directory. On AP40, we have the under OSPool, AP40, data, and then your username. So I would put my container image there. Cool. And now if I take a look, maybe. Oh no, I made the mistake of trying to tab complete. There we go. If I type this out fully, there we go. And then what I would put into my submit file, I'll just leave this as a comment. In my submit file, I would put container image equals OSDF, OSPool, AP40, data, my username, name of the container image. And this is what I would add to my submit file to make sure that this container image was used to execute my HD Condor jobs. Okay. Any questions on what I've covered so far? There's a lot of information there.
So essentially what it does is It's just telling it like take this file of this container, open it, and run everything, like all of the other, like the actual code inside of that container.
Yep, yep, exactly.
And you
Um,
don't need to do anything else apart from defining and uploading the image of the container.
you shouldn't need to. There can be some hiccups. Most common is it can't find the commands in the path. That's usually if you're installing something a bit more custom than just doing a pip install. Um, but we're happy to help you sort out those issues when they come up. Um, uh, for once, I got a crowd that actually is somewhat familiar with Conda. So, what I can describe it as, you can think of a container as being like a Conda environment, but that is just a file that you can pick up and send to another computer and it will execute. And you don't have to redo the installation command. You don't have to install Conda and redo the installation of the Conda environments. You just like physically pick that up off of as a file and hand it to another computer and it has that same environment. Um, so yeah, yeah, hopefully that all makes sense. Okay.
Thank you.
And there'll be, yeah, and there will be time at the end of this if folks have more questions. Anyone else have a question?
I do have one question. Sorry, I'm a little bit confused. So let's say I do have a Python file,
Hmm.
like test.py. How do you
Yep.
integrate it here in the container?
So you're asking a good question. I am going to deflect that until the later section about developing with a Python package. So
Okay.
what you put in the container does matter about how often you're going to change it. And something like test.py, that's something I'm probably going to change frequently. I don't want to put that in the container.
Okay.
Right. Um, okay. So scripting for the OS pool. So we understand what this OS pool is. We now know how to deploy our software packages, so our pip install packages. Um, Now, how do we actually run our Python code in this environment? So this isn't so much how to submit jobs, but more how do I set up my Python script to work in this environment? So usually when folks are writing code from scratch, especially new researchers or new programmers, they're writing it on their laptop and they're using lots of hard-coded things. So, they're manually defining the variables inside the file. They have lots of hard-coded loops in there, and they have some hard-coded absolute or relative paths. Um, and this is all based on around the assumption that the calculation is happening on one machine and at a single time, right? You just want to hit enter on your run Python scripts command once. You don't want to have to do it 100,000 times. Um, but of course, you're running one machine, so if doing it 100,000 times is going to take you a whole year, well, now you've got another problem, and that's where the OSPool can help out with. So to properly utilize the OSPool, things that are going to be changing, especially variables in your script, are probably something that you want to define as an arguments. And here, I'm limiting it to the variables that you consider as input variables. Something that is included at the start of the calculation that affects how it will run. I'm not including variable in the sense of things you may define as intermediates along the way in your script. Um, Generally, in my experience, whatever is your biggest loop, whatever is the very first iteration that you start in your script, is usually the thing that you want to pull out into the job submission. And I have an example of these things in the next slides here, so hopefully that'll make some more sense. And then relative paths, because you're going to be running on a random machine in Texas. And that machine is almost certainly not going to have /user/ Andrew.owen as a directory to operate from. Instead, I'm going to be given a temporary directory where all of my files get dumped, and that's where the execution occurs. So I need to make sure my script is compatible with that setup. And on the OSPool, this work is going to be done across many different machines. It's going to be executed many different times. So what we're really looking for here is the flexibility to use our same scripts in all of these places with minimal changes, especially to anything that's hard-coded in the script itself. Okay, so that was a lot of words that may not have actually had a lot of meaning to it. So I have an example to walk through with you to demonstrate what are these concepts and advice that I'm trying to communicate, and we'll make changes to the script as we go through. So I have an example script. It's something I wrote up just for this training. I didn't actually run it or anything, but the idea is I got this simulator.py. It's going to simulate some sort of physical system. Insert your favorite physical system. I was thinking about solar systems when I wrote this, but this could be anything. As inputs, I need a CSV file. So I have a CSV file. In there is some parameters that determine something about how the simulation is going to run, and I need to read that in at the startup here. So the issue that I'm running into as a pretend researcher is that running one of these simulations takes about 4 hours. And yes, I can do that on my laptop, and I did it a lot on my laptop while I was developing the code. The problem is if my code is working and now my professor wants me to run 100 simulations, right? Because I'm trying to explore some sort of problem, some sort of question about, what is the dependency on this variable or something else. And now I have to run this 100 times. I don't want to use my laptop for the next 400 hours, which I should have figured out what that was in days ahead of time. It's something like a month. I probably don't want to do that. No, that's not a month. That's like 10 days. I probably don't want to use my laptop for 10 days trying to run this calculation. And Danny put the right number, 17 days. Thank you, Danny. So in theory, once we've done the setup and assuming relatively modest resources needed to run this calculation, we could go from that 400 hours running on my laptop to something more like 10 hours running on the OSPool. And your mileage may vary in this case, but in general, in my experience, if the number of jobs you want to run, you can get them all running at roughly the same time. So under 100 or under 1,000 is usually this range. Then the time to finish for the whole workload is about 2.5 times the base runtime. Where does that 2.5 come from? Well, there's the scheduling aspects, there's the interruption aspect, there's a few other pieces that go into it. But in general, this is what I found in my experience. So instead of taking 400 hours or 17 days to run on your laptop, you in theory could get this done in a workday or overnight once you've done the setup. And that's really what the power of the OSPool is, and that's really what we're trying to sell people on. So here's the original version of the script that I have, and we're going to walk through the changes that I want to make to it. Well, after I introduce the script. So first I have some import statements. So I've got a custom function in a separate file, has my state class that I created, and then I need to use NumPy. And that's probably not too big of a shock to you. So my issue is that right now on my laptop, I have this long list of input files that I need to loop over. And so here's is the main loop that I was talking about earlier. I have an input file as the starting point. I need to, and I'm going to have a bunch of different simulations, each with their own input file. I have some initial position that I'm going to load from the file. So that's where I'm using the NumPy, but I mean, you could be using NumPy for lots of other things. And here, I'm loading in this input file from my data directory. I'm processing it, and this initial position is going to become an array. My state class, I'm going to initialize that with that initial position, along with a couple of other parameters. So I have some constant here. Maybe this is gravitational constant. Maybe this is something else. Noise, some sort of randomness is introduced, or maybe some sort of tolerance, and then I'm starting at time 0. So I have an initial state that I load using this initial position, and then for 1,000 iterations, I'm going to have run my state method to update with a time step of 0.01. And I realize I don't have units here. Let's pretend it's seconds, or you could pretend it's years. Really depends what physical system you're trying to model. And I have a function in here that every 100 iterations is just going to give me a status update about, the properties of the simulation that I'm running, whatever those may be. But then after those 1,000 iterations have run, I want it to give me a final report, and then I want to save that position that it's created after that simulation to file in case I want to restart the calculation at a later time. So hopefully this doesn't seem like too scary of a script here. And like I said, this is a bit of a toy example, but hopefully it resonates a lot with some of the work that you're doing yourself. So the pieces that we want to change or need a workaround, first we have 100 files in this list. I abbreviated it so it fit on the screen. And I mean, in principle, I could have done a range and defined the input file based on the range variable, but I have a list of 100 files. Okay. The other part is, let's say I get these 100 simulations to run. I know that the next thing my professor is going to ask me to do is to come back and change the value of constant to be, instead of 5.2, maybe he wants it to be 9.8. And so, constant and the noise, these two variables are something that I'm going to want to change in future runs. So I'm going to keep that in the back of my head moving forwards. And so the first actual problem, though, that we have isn't so much those things that I pointed out, but is these absolute paths. So here, when I'm reading in the input file and I'm writing out the output file, I'm using an absolute path. I'm starting from / and then I give the name of the directory or the path that I'm reading in or writing to. And that's not going to work on the OSPool. You're not going to have permission to create new files in / or in /data, most likely. Instead, what you want is to change this so that you're using relative paths instead. And relative paths just means that when you specify the location, you start from the same location as wherever this script is running. So here we do that. We change it from starting with a / to starting with a period. Period represents current directory. And then I can give the relative location to that. So with the changes I've made to the script here, I'm saying in the current directory where this is running, look for input file to load in. And when we write the output file, we want to save it to the current directory as output_name. So this is probably, I'd say, the simplest change to make, at least conceptually. May take a little practice to make sure you get the paths right, but this should be straightforward. And if you're writing a Python package in general, this is something that you're going to want to do regardless. Okay, next is, as a general rule, it's good to define input variables at the top of your script that you're working with, usually underneath the import statements. So we have these things here that we know are going to change. I know my list is going to change with different simulations. I know that these variables I want to adjust to see different behaviors. And so what I'm going to do is take the values here and create variables for them in the top of my script. So that looks like this. So I now have an input list, and where I was referencing that list in my for loop, I've substituted that variable. I have constant and noise as well, and those are also now defined at the top. And in addition to giving us, to make it easy to find the things we want to change in the file, this also gives us a central authority for what we want the value of those variables to be. So if I had another function in here that also relied on constants, I wouldn't want to have to jump through my entire file and find all the instances of 5.2 and replace them. I'd want to have a single variable that when I change it, I know everywhere I use it, the change is going to be updated. The other thing is this is going to help us make it easier to have per execution definitions of these values so that we can have things we can define at the time that we run the scripts what we want the values to be. And I think, oh, that's coming up on another slide. Next, we want to do one main thing per job. What you consider to be the main thing is kind of up to you. In general, we want to make sure the runtime is at least 10 minutes, ideally less than 4 hours. So however you divvy up your calculation to have that approximate runtime is up to you. You can also make an organizational decision. It doesn't make sense to group them. I want to keep them at half an hour apiece. That's fine too. But for our OSPool job, we want to do just one main thing per job. And in what we have going on here is this input list. So again, this input list is the main problem, right? If I try to run this script for this full input list, it's going to take 400 hours or 17 days. And that's not what we want. We want to use the OSPool to leverage that throughput. So in this case, I arbitrarily chose 4 hours as the time it takes the simulation to run because I knew that was a good number for running the job. In practice, you may need to do 3 of these simulations to reach an hour or 4 hours or something like that. In which case it's sort of up to you how you want to divide. So what I'm going to do though for this example, it's one of these CSV files per job. And so just as sort of an intermediate step, I'm going to have this list just be one thing. And I'm going to talk about how to handle the whole list in another slide. So we're coming up on it very quickly here. But the idea is that, this is what I'm going to do for a single job. And then we're going to work with HT Condor and this script to make it able to deploy all the 100 jobs that I want to run. And that leads to our next point, which is that for your input variables, it's a good idea to set up to be able to define them as an argument to the execution of your script. Okay, if you're not familiar with arguments, that may not really make any sense. So the idea is here I have these values, and I want these values to change when I run the script based on what I give it. And so I want to define these at the execution time. And the way to do that, the simplest approach, is to use the sysargv method. So the standard library package, SYS, short for system, I believe, you can use this, in particular the argv, to read in values that you define at execution time. So the idea here is that using the sysargv, we can run a command that looks like this: Python 3, name of my current script, and then these arguments that I want to define, or these values I want to define. So the file name and the values of constant and noise. And what sysargv does is load this into your script as a list. So sysargv is the equivalent of saying sys.argv equals this list of values. Now, when you actually use it, you don't actually have to define the value of sysargv. The system's done it automatically for you. But now you have this list. And if you change, the value of 5.2 to be 9.8, then what you see in this list when you query it inside the script is also going to change to be 9.8. And it's just whatever it was when you executed the command is what gets propagated into the definitions. So then this is just a list, and like any other list in Python, you can call it. So I know, so the 0th position is the name of the script that you're using. The first position is the system1.csv, and then 2 and 3 are the constant and noise respectively here. And they are going to be strings in this list. So if you're reading in numbers, make sure that you do your type conversion. So you switch it into floats, or you switch it into ints, or whatever it is that you're using here. And now whenever I execute this script, I can arbitrarily change what these values are based on those arguments that I provide at the end. I'll note that using the sysargv list is I'd say the simplest way to get started with arguments. There's a lot more advanced functionality that you can get with the arg parse module, which is part of the standard library. So if you've used a Python-based script that's been professionally developed, you do, script name -- help, and it gives a lot of information. Arg parse is one of those ways of doing it. If you're looking for a bit more batteries included, works out of the box sort of thing, you can check out the Click or the Typer Python packages, which are a bit more elaborate in terms of how they get set up. Okay, so that's the script, and we've adjusted it to work how we want. And what's really nice about this is now we can use our submit file to define the commands that we want to run per job. So first, got to introduce a submit file. Here we have the line for the container image. This is going to depend on your username and the container name that you give it, but this line with container image defines what our software environment is going to be. We then have the shell command. So this is the command that you actually want to execute inside of the job. And we'll talk about how to do this for many jobs on the next slide. But for just doing one job, I just copy and paste that command that I would have run on my terminal to run one of my simulations. And so here we got Python 3, naming my scripts, and those trailing arguments that are going to get fed into the sysargv list. We got a few other things going on here with the OSPool, because it's this very distributed system. You have to declare the files that your job needs in order to function, and that includes your main script. So in this case, simulator.py. I had that support script where I defined my state object, so my functions.py, and then there's my input data for my system that I need to include as well. Container image is automatically included in this list, so you don't have to worry about adding that. Transfer output files. So this is the thing that you want to be brought back. In this case, I know ahead of time I want this specific output file returned. If I don't know ahead of time what I want returned, I can rely on the default behavior, which is any new or changed file will be automatically brought back. Got to be little cognizant of that behavior though. If you're ever unsure, being explicit is better than not. Log is for htcondor in the job submission process, so you don't necessarily need to worry about what's going on there. Output and error. Output is going to save any of your print statements. So, in my script, I had print state dot, I forget what I called it, current status or something like that. That print statement is going to get saved to this output file, and this output file is going to be returned at the end of the job. If I run into any errors, like an exception or a stack trace or something else like that, that's probably going to get saved into the .error file. And depending on the program you're using, it may or may not. It depends which of these it'll go into. I did have the resources that I want to request to run this one calculation. So here I know it's pretty lightweight, 1 CPU, 1 GB of memory, and 1 GB of disk. Yours may differ, but that takes some trial and error to figure out. And then at the end here is the queue statement. This is kind of in a funky position, but you can think about the queue statement as essentially the equivalent of a Python for loop. Here it always has to be at the end, which is a little odd, but in this case, I'm telling it to Q1. So we're saying for I in range 1, submit jobs. So this is an example for doing one job, but of course the real power of the OSPool comes from doing many jobs. And the submit file is designed to be able to support that. So what we need to consider is what are the things that are going to change across these 100 different jobs that I want to run. And I'm sure with some thinking, you could identify these pieces as well. I know that system 1, or more accurately, that 1, is going to need to change for each of these jobs, at least for my initial run for that 100 files in my list. So I know I need to change these things ahead of time. So what I'm going to do is replace this with a variable. So I can define a variable in my submit file and use that to control its value. So very much in the same way as with the Python script, we can define a variable and put it in a central location at the top. And here I'm saying my system is defined as system1. And now wherever I have system1 in my submit file, I can go through and replace that with the HD Condor syntax for variable substitution, which is $ parentheses, name of the variable. So in Python, variable substitution happens automatically. In other languages, you have to provide some sort of syntax to indicate that it's a variable. And so here, $ parentheses is how we provide that substitution. Now, of course, so I've made a central location that defines what my system is, but I still want to loop that over 100 different files, right? I want to create one job for 100 different files. And this is where that queue statement comes in. So I need to modify that queue statement. And again, it's very much like a for loop here. So queue my system, so the variable I want to define from the list of values that it can take. And here, the list of values is just system1, system2, etc., and so on. And so now this will submit one job per line of this systems list.csv. And each one of those jobs will have a different value of my system. And so when the first job runs, it's going to use system1. Second job runs somewhere else, it's going to be using system2, and so on down the list. Okay. I'm going to jump through into the development section here, and then we'll open it up for questions. I'm running a little longer on time than I planned to. So developments, developing a Python package for the OSPool. I recommend modifying the container approach. So someone had asked about, where do I put my test.py script? Do I put it in the container, and if so, how? The answer here is to change that so that all of the dependencies that your package needs is going to go into the container, but then the actual script or package that you're actively developing does not go into the container. So the idea here is that package or that script is essentially input for the job. So it's not yet part of the software environment. It is input for the job that you may be changing in the near future. So then in HD Condor, in your transfer input files, you can change over, you can easily change, what are the files that you're sending as input for that job in order to fix a bug or some other part of the development. So this gives you that advantage of the container, which is this portable software environment. And so you'll make sure whatever machine your job runs on, it'll have that version of NumPy that you need. It'll have that version of Pandas that you need. But you don't have to build the container each time you make a change to your script. And that's really the highlight here. Things that change frequently should not go into the container image, because when you need to change the container image, you actually need to rebuild it. There's an asterisk here. Yes, technically you can edit an existing container image. It's not reproducible and it requires expertise. So I recommend that you just build it again. And so what that would look like is you've got your instructions in your definition file, you've got your development package that you're working on, and it has a bug unbeknownst to you, which is, I imagine, not an uncommon occurrence. And then you've got some data that you want to send along as well. And what you don't want to do is put that into a container, because you run the job, you realize there's a bug, you got to come back and fix your script. So you fix your script, but again, in order, whatever's in that container image, you've got to rebuild it. So you've got to know how to edit it. And this is going to start to add some headaches to your day. The example I gave earlier, it really only, I think it was like maybe 5 minutes that it built in that live demo. But some of these software stacks can get really complex. And that means, the container build could be 2 hours or longer. And that's not something you want to have to do every single time you make a change. And that's another reason why you don't want to put data in the container, even if it's not very large. If you make a change to that data, again, you're gonna have to rebuild the container. You just want to avoid this mess. So instead, what you do is, like I said, you submit the files as additional input as part of your job. So you give it the container image to HT Condor, but you also give it myscript.sh and data.csv, and those will go out as part of the job. And then if you need to make a change to the sh scripts or your Python scripts, whatever it is, you can just make that change to the script, submit a new batch of jobs, and you don't have to touch the container image unless there's something fundamentally different about how your script operates and the packages that it needs. And the same bonus applies to the data then. If the data is not included in there, then you can easily swap that out for something else as well. So this is the approach that you want to take with working with development packages or scripts that you're writing. Things that are changed frequently should not go into the container. On a related note, version control. So good programming practice is to have version control for your scripts in case you need to roll back changes or you want to make sure you have got a consistent version everywhere. So something that we recommend is that you don't pull your package inside of the job. You don't want to do a git clone inside of the job or other equivalents in your version control. So let's say we've got my version control, GitHub or GitLab or something else. And then there's the OSPool. So what we don't want you to do is submit a bunch of jobs to the OSPool, and where each of those jobs pulls from your version control system the latest version of the software. Because if you submit a bunch of jobs over time, what you're going to see, when you submit a bunch of jobs, they're distributed over time in addition to space. And so if the latest version updates in your version control, then when one of these later jobs starts up, it's going to pull this later version of the code. And now whatever was going on in this run has an inconsistency. The jobs in the first half were using an older version, jobs in the second half are using a newer version, and that can cause you headaches because of that inconsistency. So we want to avoid doing this. Yes, you can pin the versions. You can even pin like, hey, I'm only using this specific commit to my version control system. But keep in mind, it's very easy to submit thousands of jobs on our system, which means it's very easy to piss off the server that's hosting your version control. Because if you're querying it 1,000 times an hour or something like that, best case scenario, you get rate limited. Worst case scenario, they block the network entirely from accessing their server. And then if you're using an authenticated version control system, you shouldn't be sending out your credentials per job, just as a general principle. And that goes back to the open and trust relationships that we have inside the OSPool. If you don't want random sysadmins be able to log into your GitHub, you should not send your GitHub credentials along with your job. Okay, so what is the recommended approach? What I say is sync whatever it is to your access point first, and then you explicitly include that as inputs for your job. So the reason this works nicely, so from your version control system, you do the latest pull or you download the latest version, you put that on the access points, and whatever you put there on the access point, unless you change it, it's not going to update without you looking at it. So what that means is you can then use it as input. You submit a bunch of jobs, and let's say that a new version is released behind the scenes while you were submitting this workflow. Jobs later on in the workflow after that release, as long as you don't update it on the access points, then you're going to be using that same version of the package throughout the whole workflow. So and another advantage here is that you can just, if you are using authenticated version control, you can just copy the files to the access point. You don't have to authenticate on the access point, although that's up to you. The trust relationship is a lot more secure with our access point than it is with our sites. And then the other thing is that by including it as input in the job, you get to leverage all of our infrastructure for distributing files in a high throughput nature, right? The OSPool, HD Condor, it's all designed for this idea of lots of independent jobs just geographically distributed across the country. That's not necessarily true of your version control system, which is on your lab computer. That may not be able to handle, you know, thousands of queries an hour as you try and pull updates from it across all these different jobs. Okay, so wrap up with some next steps here, and then I'll answer some questions. So we do have an exercise about, it's a relatively simple one that uses Python. And so this is an opportunity to look at what that pre-installed Python approach looks like. You know, what does it take to use the Python that's already installed on the machine? And this also just demonstrates, you know, job submission and how to set up your script to work in this sort of environment. So if you want something hands-on, this is what I would recommend as some practice here. If you don't already have an OSPool account, you can submit one through our website. So we have an account request form on our website. You're welcome to submit one. We also have a test instance, so guest access, where you can do some simple jobs through a Jupyter interface. If you have any questions, I'll happy to answer them after we're done here. Plan for resilience and scale. So I've hinted at this throughout. OSPool is a diverse system, lots of machines, lots of workloads. Issues do pop up at scale. So what we recommend is that you test one job before you try to run 10. You test 10 jobs before you try to run 100. It doesn't have to be every order of magnitude, but you want to do some testing at a small scale before running a large batch, just to make sure you've ironed out most of the bugs. Issues may crop up in the larger scale, but as long as you are scaling up slowly, you don't have to worry about them too much. Another thing that's a common issue is, you know, you need extra space for all your output files. Folks don't think a lot about, oh, it's just a 50 megabytes as an output file. But when you multiply that by 100,000, you're now talking about, I can't do math in my head. What was that, 100 gigabytes? You're talking about a lot more data now. So think ahead about what that is. And then for running your jobs, you know, think about how do you monitor, how do you organize, how do you catch failures and rerun failures and things like that. There are a lot of options with HD Condor that will help with all of these aspects. But if you're looking for them or want some help, please reach out to the facilitation team. We're happy to help. And that leads to this end slide here. Send us an email, support@osghcc.org. We also have twice weekly office hours, Tuesdays and Thursdays. Actually, we have an office hours coming up here in 15 minutes. So we'll include the link for that once we're done recording. And we got lots of guides on our website. I'm going to put a feedback link in the chat. So we'd appreciate your feedback. If you have any suggestions or comments about the training, we do read your feedback and we will try to incorporate that to future trainings. Yeah, and then OSPool and a lot of our work is funded by the National Science Foundation, but we do not necessarily reflect the views of the National Science Foundation. All right.